And we're back. Season 1, Episode 3. Huge podcast coming in. Sorry it actually took me so long to get this podcast recorded. I was at a conference in Montreal, Canada. I live in America, so it was a little bit of travel time. It was like a 4-day conference, so I was pretty busy last week. But what's good news is it was a conference on what I wanted to talk about today. Specifically nanotechnology and cancer therapy. So this is actually my specialty. I've got a lot of training in nanotechnology, specifically treating cancer, and so that's why I wanted to talk about it. I think it's a really, really cool industry. We're kind of on the cutting edge, the frontier of just figuring things out still. So it's a really cool, fun industry where you're on the front lines of science. So yes, I want to talk about nanotechnology specifically to treat cancer. And again, I'll just be I'm playing Discipline Priest in World of Warcraft, healing Mythic plus dungeons as we're talking about this topic. I'm trying to think if I'm forgetting anything else. Next week, actually, next episode, I'm going to have a visiting speaker. I don't know the format of how we're going to pull that off just yet. It's going to be over Discord somehow, but also the speaker doesn't know the format that I'm doing this podcast on. She has no idea that I play World of Warcraft, so that whole thing is going to be kind of funny, but it should be good. So next week, or next podcast, I'm not exactly sure. I hope it's next week. It's going to be on DNA editing, gene editing. We'll talk about that next time. This time, though, we'll sort of mention genes and whatnot, but we're not going to talk about editing. We're just going to talk about nanotechnology, and that'll give you like a foundational knowledge for next episode. So first, nanotechnology. What is that term? Whenever I see it in like a news headline or something with no context, and so it kind of has this mysterious sort of vibe to it where in my mind, before I kind of got into this industry I'm in, I pictured like little robots floating around in the blood or something. And I wish we were to that point. Maybe someday we'll get to that point, but we are not. That is not what nanotechnology is just yet. So we'll talk about, we're not quite to little robots, but we can do some cool things. And I'll just talk about specifically nanomedicine. So if you say the word nanotechnology, it's sort of analogous to saying like automobiles or something, where it's like a very general term where you need more descriptors to add context. So nanotechnology, there's a bunch of different pillars of that. I'm just going to be focusing on nanomedicine. So nanotechnology to treat disease. So these are systems that we actually put into the human body to try to treat a disease. And the disease that most nanotechnologies focus on is cancer, because cancer is so prevalent. And Big Pharma, there's a lot of money for Big Pharma if they can find a technology that cures cancer, right? So there's a lot of money in it. You can save a lot of people's lives, obviously. Yeah, just getting people better therapeutics in general so that we can sort of get away from this whole idea of chemotherapy. And we'll talk about that. So first, like nanotechnology or nanomedicine, we got to get an idea of the size of that. What does that nano mean? Well, if we consider a cell, just like a cell in our body, if I were to swab my cheek with a cotton swab, say, and then pull those cells out and look at them under a microscope, those cells would be... Holy nuggets, this is a pull. Huge pull right here. Okay, those cells would be observable under a microscope. And that's what we call like the micro scale, where it's a micrometer. So it's pretty small, right? Cells are small. We know they're small. It takes a microscope to see them. Well, nano materials are 1,000 times smaller than a cell. So you can't even see them on a microscope. You wouldn't even know they existed. So that means if you cut a cell up into 1,000 pieces, one piece would be about the size of a nanomedicine. So they're very, very small. And because they're so small, they can actually get into the cells and cause some kind of effect. And that's kind of the whole idea. So these things are very small. They're on the nano scale, very small scale. And then in order to sort of understand what they do, first we just need to understand cancer a little bit. So I just wanted to have just a quick discussion on cancer. You know, what is cancer? We're all, honestly, it's so prevalent that, you know, cancer's been in my family. It's affected my family. It's probably affected almost everyone's lives to some point, like family or extended family. But what is happening, or why can we not find the cure for this damn disease? Like, what is it? What makes it so hard to cure? Well, in order to sort of understand that, we have to just talk about cells for a second. So every cell in our body has genetic material, right? Has all the information that makes you, you. But every cell does not use the same DNA. It has all the same DNA, but the DNA that gets used is different. And they just and so that just means genes, like all the different genes that are being expressed are different from cell type to cell type. But every cell in our body has to replicate and divide for the most part. And that means they have to make a complete perfect copy of their genetic material. And DNA replication inherently is not perfect. So every time we go to copy, every time a cell goes to make a copy of its DNA, there's going to be imperfections. 99.99999% of the time those imperfections do nothing. And then even more rarely than that, the imperfections just lead to cell death. The cell can't survive with that mutation. And then very, very rarely, the mutation actually leads to what we call cancer. Now, what does that mean? You know, how do we wrap our heads around that? Well, what has to happen is a mutation. So all the cells in our body, they have like a clock, an internal clock that where they're dividing based on this sort of internal clock, and they stop dividing when they don't need to divide anymore. Well, a mutation can happen anywhere, so it can happen in the pathway that's regulating how much they divide. So if that happens, and the cell just starts thinking, oh, I need to divide continuously. I need to divide now. I need to divide again. I need to divide again. I need to divide again. I need to divide again, just forever. Mutations start to build up, right? Because we're just copying our DNA over and over and over. And so that leads to more and more mutations. And then eventually what's going to happen is a mutation that is a mutation in like our immune system stoppage point, where our immune system is keeping our cancer cells at bay. They're like, okay, we're fighting it, and then all of a sudden a mutation happens that disallows that recognition of our immune system to the cancer cells. That's when it becomes a problem. So now the cells are already dividing too fast, and now our immune system can't recognize them. Our immune system doesn't realize that they're a problem, and our immune system allows them to keep growing. So that's what that's the definition of cancer. Where they have avoided the immune system and they can divide indefinitely. Now any cell can do that, right? It just takes the right mutations. So that means any cancer, so any tissue in the body theoretically then can get cancerous. And so there's so many different cancers, and every cancer is in a different tissue, and every tissue is unique. And so there's going to be different mutations in every single cancer. And so all of a sudden it just becomes this huge problem of like, okay, one medicine is not going to cure all of these cancers. It's too diverse. There's too many different mutations, too many different cell types. The cancers are all different. From even what's so interesting and sad at the same time is that 2 tumors in the same patient, 2 exact tumors of the same cancer in the same patient will respond to therapy differently because they have different mutations, just subtle changes from tumor to tumor, even within the same patient. That's how hard it is, you know, because all the mutations are so unique. So that's how big of a problem it is, and that's why it's so hard to wrap our... You know, there's never going to be one cure. There might be, actually. I don't want to say never, but we are so far... I should just couch it as we are so far from a one treatment fixes everything approach. So as we approach it today and right now is kind of cancer by cancer, disease by disease, tissue by tissue to treat the cancer. Yeah, and so it's hard. Survival rates are, you know, they're getting better year over year as we're understanding, you know, better, as we're coming up with better chemotherapies, better nanotechnologies, immunotherapies, some of the stuff we talked about in episode 1. Yeah, so we are getting better, but yeah, there's no definitive cure for cancer as we know it yet. But, you know, there's promising things, and so we'll talk about a few of them. So let's just rewind to maybe, I don't know, 1950 or something. So if you got diagnosed with cancer in like the 50s or the 60s, your only option was chemotherapy. That's it. And what that meant was we're just going to we're going to inject into your blood, into your veins, a small molecule, a drug that, yeah, it's really good at killing fast-growing cells. So it's going to kill cancer cells. But it's also going to kill cells that... Oh, got a death. It's going to kill all fast-growing cells in the body, right? Because it's not specific to cancer. It's any cell that's growing fast is going to get affected. So that means hair cells, cells in your gut, like in any mucus lining, cells in your mouth. We know our mouth, you know, if we get a cut in our mouth, it heals really quickly because the cells divide really fast in our mouth. The cells on the palms of our hands, because our hands, you know, are sloughing cells all the time. Oh, I don't know what's happening here. So all of these cell types get affected when you just inject chemotherapy into the body. Gosh, I got silenced. This is a freaking nasty pull. I don't even know what's happening. Oh! Okay, we're fine, I think. Are we not fine? No! I think we're gonna die. Okay, we didn't die. Not a wipe, not a wipe. Okay, so we had a situation. But I think we're gonna make a full recovery here, I think. And there's a YouTube component to this as well, so if you want to check out the YouTube video of the actual healing and stuff. We got behind on explosives there. We had some deaths, but we're chilling. Okay. Sorry about that little sidetrack. Okay, so kind of forgot where we are. Okay, yeah. So we're gonna inject you intravenously with an IV or something. We're going to give you some kind of chemotherapy. It's going to circulate in your blood. It's going to get into a bunch of cells, bunch of tissues in your body. Cells that are dividing rapidly, they are going to get affected the most, and we're going to kill those cells the most. But it's going to get into all sorts of tissues. We can't control it. So there's going to be a lot of toxicity. There's going to be a lot of side effects. And it's typically the toxicity that requires us to stop treatments. it's not like we cannot just keep giving chemo over and over because there's some toxic limit where yeah, the patient just can't handle any more chemo. That's usually the stopping point. Either we cure the disease or therapy just becomes too destructive. So lots, and you know, we've realized this for decades, lots of effort has been put into finding ways to decrease off-target toxicity. How do we show the chemo where to go? How do we show it the cancer cells so that it doesn't just get into every cell in the body? And that's where nanotechnology, this idea of nanotechnology, comes in. There's a few ways we can approach it. We can either, so just generally speaking, if we needed to decrease toxicity on a fundamental level, we could potentially, you know, change the structure of the chemotherapy a little bit so that it's like maybe a little less toxic, or it can target specific cells a little better or something. So we explored all of those avenues for sure over the last few decades. And then the first sort of nanomedicine that came online were these things called prodrugs, where the drug is injected as an inactive form. So it has no activity initially until some kind of chemistry occurs. Usually something gets cut off of it, like we've attached on some molecule that we know an enzyme in our cell can cut, and it'll cut that molecule off, releasing the active drug. So that's a prodrug. And there's been a lot of, you know, good benefit of a prodrug. What's good about a prodrug is it's inactive. We inject an inactive form of the drug until it becomes activated in the body. It's not going to cause any side effects. It's not going to do anything. It'll just get cleared, go through the kidneys, urinated out, no toxicity. Those are what we call prodrug. The other option is the field I'm in, is we deliver the drug, the chemotherapy, with some kind of delivery vehicle. And that's the terminology. I'm not making that word up. So we design delivery vehicles to carry the drug as our cargo. So we call the drug our cargo, and the whatever we're packaging the drug up into, that is our delivery vehicle. Kind of funny. I like the terminology, honestly. And so what are these delivery vehicles? What does that mean? Well, we take this toxic drug that we know is going to get into tissues that we don't want it to get into, and we're just going to package it up. We're going to encapsulate it in, gosh dang, something like a particle, a nanoparticle. So again, these really small particles. We just package it up, get it inside of these particles, and now the drug is stuck, localized in these particles. Can't get out, can't do anything. And it's not going to cause any toxicity, right? Because it can't do anything. And we design the vehicle to have either some kind of release mechanism, or maybe the particle can be degraded, and release the drug once it's degraded. And so once we use that term degradation, I think you can kind of get the ideas to what we'll be talking about. So these are polymers, polymeric, typically polymers. It's either polymers or metals that we can encase or encapsulate drug into. So what that means is we get, like, drugs typically don't like water. They don't like to be in water. We call them hydrophobic, water fearing. they're not soluble. You can't get them to dissolve. Well, we can use that characteristic to get them stuck inside a particle that doesn't like water either. And so we can pick a polymer material or some kind of just material that is hydrophobic, doesn't like water, and then we put the drug and that material in water. We put those two things in water. They don't like water, so they're going to stick with each other. They're going to be like, hey, I don't want to have anything to do with this water. Let's stick with each other. Yeah, and we'll keep each other friends. We'll just hang out with one another. And what happens is it's sort of like aggregation, where the polymer will just sort of crash. We call it crash out of solution, where it falls out of solution, where it's not soluble in water. And as it falls out of solution, it makes these like really small particles. And inside those particles is the drug, encapsulated drug. And so then we can decide what polymer to use, what material to use. We can use all sorts of different polymers. Polymers that are degradable, polymers that are not degradable, polymers that have some kind of stimulus, like maybe they're stable until they get into acidic environments, for example like the stomach or something. Like if this material is very stable until we put it in the stomach, and then it's going to degrade because the acid in the stomach is going to be hard for it to survive. Things like that. So the idea is, for nanomedicines, we're encapsulating a drug inside of a vehicle so that we're masking the toxicity of the drug. And then what's awesome is what I work on specifically. You can then do some chemistry on the surface of these particles. So these particles are very small, right? They're 1,000 times smaller than a cell. So they can get into a cell. But we can change the chemistry on the surface as well. So we can potentially add molecules that tell the particle where to go. We call them targeting motifs or targeting molecules. So we can encapsulate a toxic drug in the middle, and then on the outside we have like molecules that tell the nanoparticle where to go. We use antibodies, we use proteins, we can use a bunch of stuff that sort of decorate the outside, so that when the particle bumps into a cell that we're targeting, it recognizes, oh hey, this is where I need to go, right? And then it can get inside that cell, and then hopefully we've built into our nanotechnology the proper drug release. Wow, that guy just died. I don't even know what he died to. We can build into our nanotechnology the proper release system. For example, if I made a nanoparticle, are we skipping? We are indeed skipping. If I made a nanoparticle, we're doing a weird skip right here. Sorry, I'm getting sidetracked. Okay, so if I design a nanoparticle out of a material that is sensitive to acid, the idea then would be, and then I put on the surface of my nanoparticle a targeting motif that targets some kind of protein on a cancer cell surface. And I put like a drug, like a chemotherapy, doxorubicin or something, into the core, the center of this particle. Sorry, just healing. So the idea of this system then, this theoretical system, would be we inject it into the blood, and now these nanoparticles are floating around. They're going to just bump into cancer cells. Eventually, you know, as blood goes through the body, they're going to bump into the cancer cells, and they're going to recognize the proteins on the cancer cell surface and go, aha, this is where I need to go. So it'll bind. The cell will take up these nanoparticles. The drug's going to be inside. The cell has no idea there's drugs inside. And what cells do when they take up things is they just send them for degradation. Send them into the lysosomes. Very low pH, very acidic in there. And we're just going to degrade it, spit it out as little pieces. So it takes up these particles, sends them to the lysosomes for degradation. Well, that's the trick, right? Aha. Well, now, as you degrade these particles, drug is released, right? And that's the whole idea, is like we're using some kind of stimuli responsive nature of this material to release a drug where we want it to. In this hypothetical scenario, we are using like a pH sensitive vehicle to release a drug in the lysosomes. So a cancer cell will take up these particles, send them to the lysosomes as it would with anything else. Well, that's exactly what we wanted. That's exactly what we were expecting and hoping for. And then as the cell is degrading the particles in the lysosomes, drug is being released. That drug is then free to act. It can kill the cell. And what's nice about it is we're only killing the cancer cells. So it gives us some specificity, right? Instead of just injecting small molecule chemotherapy into the blood, we now have a built-in method to release drug where we want it to. And we call it, like, another synonym for it is smart technology, where the smart is kind of the scientist thinking up like a good method to deliver the drug, and then they're just picking the material that suits their needs, right? Because we have materials that are sensitive to anything. And so as long as you can think up an application or like try to be clever enough to come up with a way to release drug, you can make a nanomedicine. It's something I've spent a lot of time on myself. Coming up with like different methods of like, you know, different materials to use. So for example, I'll give you another example. The material I used in my first paper that I published, I used a polymer that was sensitive to UV light. So you shine UV light on these nanoparticles and they spontaneously degrade. So that was my triggering mechanism. So I loaded a few different drugs, chemotherapies, into my particles, and then I showed I could stimulate the release exactly when I wanted to, and it was whenever I shined UV light. So there was no free drug anywhere in the system until I shined UV light, and the particle would degrade, fall apart, and drug would be released. And so I showed, at least in cells, that you could use this triggering mechanism to trigger cells to die. Once the cells had uptaken the particles, you just shine 10 minutes of UV light on them, and the cells would die because the particles would degrade and the drug would get released inside. Now, how applicable is UV light to real life cancer therapy? You know, it's probably not super applicable, but it's just like a proof of concept type experiment, because I also made ones that were responsive to hydrogen peroxide, like reactive oxygen. And that becomes a little more applicable because there's a lot of reactive oxygen in things like lysosomes. It's really acidic. There's lots of, reactive oxygen species. So if you can get your particles into the lysosomes with hydrogen peroxide responsive materials, same thing. You can trigger degradation in these lysosomes. And that is how nanotechnology works. We're just looking for ways to mask toxic chemotherapies from the body so that we don't get these off-target toxicities. And then we can treat with a higher dose, or we can treat for longer, and we don't have to worry so much about off-target toxicity. in theory, right? But that's the whole idea. Now, there's all sorts of different flavors of nanomedicines. I've specifically just kind of focused on nanoparticles because that is my expertise and my training. But what we talked about last week with liposomes for, you know, like vaccines or basically any drug delivery, though lysosomes are also a nanotechnology. Just slightly different form. So instead of a polymer nanoparticle, a liposome is just a fat droplet. But it's the same idea, right? We have a cargo. In the case of a liposome and a vaccine, we have mRNA as our cargo. So that's like our therapeutic drug. And we've encapsulated it inside a delivery vehicle. And that's not because the mRNA is toxic. That is because the mRNA is not stable. It will just degrade instantly in the body. So we're using a nanotechnology to kind of stabilize the mRNA, basically, until we can get it into a cell. But it's the same idea. So with the mRNA vaccines, I almost just died. We are getting the mRNA into a macrophage. So the macrophage will take in these liposomes, break them down. As they break them down, mRNA is released, and then the macrophage just, oh, here's some mRNA, let's turn this into a protein. It doesn't know the difference that it's not its own mRNA, so it'll just turn it into protein. Well, that protein's the spike protein, and so we can start making antibodies against the spike protein. Same idea with drugs in polymer particles and nanoparticles, except all we're doing is masking the toxicity of the drug. So there's no free drug floating in the body. It's all encapsulated in these nanoparticles, and then only when the nanoparticle is taken up by a cell, the cell will send it to the lysosomes, chew it up, drug gets released, and that's like our that's our nanomedicine. That's how it works. So we have nanoparticles, we have liposomes. Oh, I didn't even loot my chest. What else is there? There's like, so if you use a polymer that's water soluble, you don't have to turn it into a particle. It'll just dissolve in your blood. And so you can attach drugs directly to a polymer. That's like kind of that idea of a prodrug, where the drug is not active because it's attached to attached to a polymer. Only when the drug gets cleaved off or cut off from the polymer does it become active. And so you can make, you know, stimuli responsive linkers or chemistry to release the free drug. Those are just like linear polymers. That's another form of nanomedicine. The biggest thing I think in the industry right now are these things called antibody drug conjugates, where we're kind of taking the whole nanoparticle out of the equation and we're just using the targeting motif and attaching a drug directly to the targeting motif, where the antibody is the targeting motif. It'll recognize a specific protein on a cell, and we've attached drug to it. Same idea though, the drug is not free floating in the blood, it's attached to an antibody, so it's not toxic. And then as the antibody recognizes its target cell, binds on the surface, the cell will take it up, try to chew it up in the lysosomes. As it does that, free drug is released inside the cell. Let me think of other applications. Oh, so you don't have to use polymers, you can use metals like gold. So gold nanoparticles, a big field. I don't think there's any FDA approved gold nanoparticles. There might be, so don't hold me to that, but I can't think of any off the top of my head. There's for sure some in clinical trials. I know there's probably some approved for like imaging, but basically you just put these really small gold particles in the body and you can do the same thing. You can attach drug to them, you can encapsulate drug, you can do a lot of stuff. That's not really my field though, so I don't want to talk too much about that. I'm just aware of it. I went to the conference today and there was a lot of talk on these things called, this was completely new to me, but these things called microbubbles, where you're generating very tiny bubbles, just air bubbles, and inside the air bubbles, or somehow associated with the air bubble, I think there's like some surfactants. You can use them as a delivery vehicle. And I don't know much about that, so that's something I need to look into more. But that is the whole idea of nanotechnology, where we have these drugs that are super toxic. We don't want them getting into all the tissues in our body freely, because then they're just going to cause toxicity problems, lots of side effects on chemo. So we're going to package these things up, these drugs, these toxic drugs, we're going to package them up into these little nanoparticles. And then we've designed the nanoparticle system to have a specific release mechanism. So and then also we usually have some kind of targeting mechanism, so we can target a specific tissue or a specific cell type. And then we can get the toxic drug to the tissue or to the cells that we're targeting. And that is nanomedicine in a nutshell. Lots of different opportunities, kind of like, if you can imagine it, you can try it and you can do it and see if it works. And so there's a lot of people working in this field. There's so many ideas out there, and there's so much to be discovered still. We're definitely just the tip of the iceberg. So really cool industry. So it's not little robots in the blood doing things just yet. Right now we're just kind of using chemistry, clever chemistry, and clever biology to release a toxic drug in a tissue that we want. But, you know, there's a lot more advanced options coming down the road. Coming down the pipeline for sure. So yeah, that's what I wanted to talk about today. Hopefully that was coherent, because I don't even remember that dungeon. I feel like there was a lot going on both ends. Me thinking and me healing a dungeon. Next week, I'm excited. I'm going to have a visiting person who knows a lot about gene editing. So we're going to talk about gene editing. It's definitely the future. And specifically gene editing, so if we think in terms of cancer where there's all these different mutations, if we can come up with one gene editing technique that works kind of as a platform or like a broad scale, theoretically we can just use that one genetic technology to change any gene we want. And then we could cure any cancer type that we want, because we just, you know, we can just change what gene we're targeting, but use the same platform technology. And that's we're far from that, but you know, that's on the horizon perhaps. And we'll talk about that more next week. But yeah, thanks for listening. Hopefully these are enjoyable. And you can check out the YouTube channel. Same thing, Odette the Priest on YouTube. And you can see the Mythic Plus side of things if you're interested. All right. Peace. Thanks for listening.